Today what we're going to be working on is continuing to look at how derivatives affect the shape of a graph. And I also, why am I still wearing this stupid thing? We're also going to be looking at some slightly more complicated examples of curve sketching that we can do. So I told you we would get to more complicated examples, but before we do that, I want to introduce a couple of new topics and in particular, look at how the second derivative can help us out, because it's going to kind of really tie everything together that we have. So the first thing that I want to introduce is the notion of concavity. Now, in general, concavity is defined in the following way. We will say that a function f of x is concave up on some interval a to b if for any x1 and x2 in a to b, the secant line through the points, and I'm sorry, I'm writing this really slowly, x1, comma, f of x1, x2, f of x2 is above y equals f of x. And f of x being concave down, basically it's the same definition, but the secant line is below. Now, that's a really kind of cumbersome definition to work with. I mean, it's a perfectly fine definition, actually, I should say. Like, as definitions go, it's not really that complicated. You check to see whether these lines are above or below, and that's all you're doing. The problem is that in practice, it's complicated to use because you got to check all of these different lines, and how are you going to go about doing that? Well, you can do it in some cases, but it's not necessarily really very easy to do in general. It's often pretty easy to geometrically see that this would be true in some cases or not true. You know, like you can kind of visualize from the graph very easily. Do all these secants lie above? Do they lie below? Like if I give you a picture like this, once I have some space, if I give you a picture like this, it's fairly easy to see that over here, all of these secant lines are going to sit below the curve, whereas over here, all of these secant lines are going to be above the curve. So this part is concave down, which I will just abbreviate with CD, whereas over here, we are concave up, which I will abbreviate with CU. So you can visualize this kind of thing, but to prove whether or not you've got something that is concave up or concave down is a bit trickier. So here is going to be a nicer way of thinking about concave up and concave down when we are dealing with differentiable functions. So for a differentiable function, we can actually say if f is differentiable, then the following holds. If f prime of x is bigger than 0 on the interval from a to b, f is concave up. If f prime of x is less than 0 on a to b, f is concave down on that interval, of course. Because, like, remember, in general, you can... Why in the world is this having so much trouble focusing lately? It's driving me nuts. I don't understand why the glare is, like, worse now or something than it used to be. At least I feel like it is. Anyway, obviously, it only holds on that interval. You can have the concavity change many, many times. And we will refer to points where concavity switches These are known as inflection points. For our function f, of course, because, depending on what function we're looking at, that's going to determine what inflection points we've got. It's not like there are certain points that are always inflection points or something. Anyway, so if your function changes which direction it is concave, then it's going to have an inflection point there by definition. Now, I'm not going to prove this. The proof is a little bit technical, and it's one of those things that's not that bad, but it's not like you really feel like you've really necessarily accomplished much by the end of it, because sometimes I do like to show you the technical proofs even if they're obvious. For instance, the mean value theorem. The mean value theorem is one of those things that's obvious, but it takes a bit of work to prove. And we did that. We did that proof. But this time, this is sort of obvious, and I think we've seen enough proofs of obvious things that I'm going to kind of skip over this one and not worry about it. If you're really interested, I'm happy to talk to you about it, but I think I'm just going to let you kind of accept this, and we'll use it without a full technical proof. So the thing is, essentially what you do is you show that, because f prime is increasing, the slope of the tangent is continually increasing, and therefore this f of x plus h over f of x. But it's a very technical and annoying sort of proof that you have to do. In fact, I think there's better ways of proving it that use techniques we haven't quite encountered yet. So that's another reason why I want to skip over it. I think I could prove this more easily with some of the techniques later on. But intuitively, it's kind of clear why this should be true. If your tangent keeps increasing, then you must be turning in the upwards direction. And if your tangent line's slope is decreasing, then you must be turning in the downwards direction. So really, concave up, you can think of this as turning upwards, and concave down is turning downwards, at least if we're talking about differentiable functions. Now, why does this matter? Why are we interested in this? Well, there are two things that make this very interesting, okay? Actually, there's more than two things. One thing that makes this interesting, before we get to the two I was first suggesting, the first thing that really makes this interesting is it tells us something about the shape of the graph. If I know that this thing is curving in a certain direction, that helps me make a more accurate sketch. But the other two things, the places where this connects back to the stuff we've been studying, think about what happens at a local minimum or a local maximum. One second. At a local minimum or a local maximum, what kind of concavity are we going to have? Well, assuming that the function is differentiable, actually, even if it's not differentiable, we can still say some things, but I'm going to focus on the differentiable part here. Let's suppose that we have a differentiable function and it's got a maximum. Well, just visually, you can see it's going to have to be concave down here. It's turning downwards. And at a local minimum, it's going to have to be turning upwards. So you'll notice that a local maximum, if it's concave down, then it's got to be a local maximum. And if it's concave up, then it has to be a local minimum. Okay, so if we can figure out the concavity at a critical point, and the function is differentiable, because that is important, it's got to be differentiable, otherwise this doesn't work. But if we have a critical point where the derivative exists, therefore the derivative is zero, and we can figure out the concavity, well, then we can determine, is this a local maximum or a local minimum? So is there a good way to figure out the concavity? Well, the answer is yes, actually. If the function is both differentiable and its derivative is differentiable, then we can easily figure out the concavity. And why is that? Well, think about it. I just said a minute ago that concavity can be determined for differentiable functions by whether the derivative is increasing or decreasing. But what do we know about increasing and decreasing of functions? Well, in general, if the function is differentiable, then if the derivative is positive, the function is increasing. If the derivative is negative, it is decreasing. So here's what we can say. Suppose f is twice differentiable, i.e. f double prime of x exists. So if two derivatives exist, we call the function twice differentiable at that point. And if two derivatives exist on a whole interval, then we call it twice differentiable on that interval. Now, obviously, functions can be twice differentiable on part of the domain and not all of their domain, but we're going to focus on the portion of the domain where it is twice differentiable. Then, if f double prime of x is bigger than 0 on some interval, f prime is increasing, so f is concave up, and if f double prime less than 0 on some interval, then f prime is decreasing, and you can probably see where I'm going with this. F is concave down. And there we go. So the second derivative actually gives us a lot of important information here. It tells us about the concavity. And not only does that tell us something about the shape of the graph in general, but this also allows me to determine whether something is a local maximum or a local minimum. If I find the critical point, I can just decide, is the second derivative positive or negative at that point? And it tells me the intervals of concavity, and it tells me the maximums and the minimums. And it tells me the inflection points. So what I want to do here is, oh, and by the way, using the second derivative to classify critical points is the second derivative test. So what we do is, if we have a critical point, we are going to go ahead and see if we can fix this glare problem, first of all. If we use the second derivative at a critical point, we call that the second derivative test. Now, couple of things to notice here. The first thing about the second derivative test is that it is nice because what we have is, well, we've got a situation where we just have to evaluate the function, the second derivative at a single point. So our other tests about critical points, they require evaluating at multiple points, and that makes them somewhat more complicated. We have to do a little more work. The other thing that's really nice about the second derivative test, all I have to do is decide whether it is positive or negative. I do not have to evaluate it necessarily. Sometimes you may find it's just as easy to evaluate the second derivative, but sometimes it's actually quite easy to make an argument, oh, this has to be positive or negative, therefore we're done. Now, there is one downside to the second derivative test, which is that it can fail. If C is a critical point for f, and f double prime of C is equal to 0, the test is inconclusive. And we gotta use another test. So this is the one problem with the second derivative test. Now, just to show you really quickly this idea of the second derivative test, let me give you like the most basic possible examples of it in some sense. So like if I have f of x is equal to x squared, you know exactly what this looks like. It's a parabola. It's the standard parabola. Obviously, it has a minimum at x equals 0. But if I want to show you how to do this with the second derivative test, well, f prime of x equals 2x. F double prime of x is equal to 2. So f double prime evaluated at 0 is equal to 2. That's bigger than 0. Thus, 0 is a local minimum. Now, here's the problem. Like I said, you get these situations where the second derivative could be equal to 0. And then this whole test fails. So here is an example where it fails, okay? What if f double prime of x were equal to x cubed? Well, in this case, interestingly enough, what we have is, I'm sorry, why am I saying f double prime? What if f of x were x cubed? Then f prime of x is going to be equal to 3x squared, which means f double prime of x is going to equal 6x. Now, the critical point of 0 that we get, because 3x squared, 3 times 0 squared is 0, f double prime of 0 is equal to 0. And when you check this using the first derivative test, you find, well, the first derivative is 3x squared. The first derivative is positive on both sides of this 0. So actually what's happening here is that we are increasing on the entire minus infinity to infinity real number line. 0 is neither a max or min, nor min. English grammar, I think technically that's supposed to be a norm. Anyway, it's not a maximum, it's not a minimum. And in terms of inflection points, what we notice is that we do get an inflection point, because you'll notice that f double prime of x is less than 0 when x is less than 0, and f double prime of x is bigger than 0 when x is bigger than 0. So what we can say is that we are concave down on minus infinity up to 0 and concave up on 0 to infinity. And that means, and I do not have any room to write this here, but 0 is an inflection point. So you'll notice that we could not classify this just because the second derivative was 0. Now you might wonder, well, does that mean though that if it's 0, that it's neither a local maximum nor minimum? No. The second derivative could be 0, and yet it's still a local maximum or minimum. So I want you to take a minute to think about this and see if you can figure out what happens with this example. So, pause the video once I write these down and think about it for a minute. What about f of x equals x to the 4th? What can we say about the critical point here? Okay, so did you figure it out? Hopefully, intuitively, you know what this thing looks like. This thing looks like a fat parabola. Well, the base is kind of a fattened parabola. The top is a thinned out parabola. If I take the derivative, f prime of x is 4x cubed. F double prime of x is equal to 12x squared. Excuse me. And then what we can say is, well, the critical point is still 0. But the problem is that the second derivative is 0 at 0. However, if we use the first derivative test, we see that f prime of x is less than 0 when x is less than 0, and f prime of x is bigger than 0 when x is bigger than 0. And therefore, what we have is 0 is a local minimum by the first derivative test, which we talked about previously. And when you check the second derivative, you see that the second derivative is always positive except at 0, but it never changes signs. So this is actually just going to be concave up on the entire real number line. And then, of course, we see that it's going to be decreasing when we're less than 0 and increasing when we're bigger than 0. So we can see here that the second derivative test is not something that is guaranteed to always work. But here's the good news. When it does work, it's really easy, and it's usually pretty easy to try it and see if it works. So I always recommend using the second derivative test first, and then if it doesn't work, we can go on to the more complicated methods. All right. Now, some other things that we should notice, by the way, is that a lot of different stuff kind of plays into each other, okay? Like, if you know certain things about whether a critical point is a maximum or a minimum, then you know other things as well. Like, let's say that I have a function, and here's a couple of critical points, C1 and C2, and there's no other critical points in here. Let's suppose that I classify this as a maximum and this as a minimum. Well, to get from a local maximum to a local minimum, I have to decrease. There's no other option. I have to be decreasing on the right-hand side of a maximum, and I have to be increasing on the right-hand side of a minimum. There we go. I finally got my right and left worked out. So if I know that I have a maximum, then I know that I'm going from increasing to decreasing. If I know that I have a minimum, I know that I'm going from decreasing to increasing. So if you can find the maximums and minimums in some way, then you really don't even need to worry about finding increasing and decreasing. That's already given to you. Conversely, if you knew that we go increasing to decreasing to increasing, then we could conclude, this must be a maximum, this must be a minimum. Okay, so it goes both ways. And the point is that there's a lot of redundant it's not that there's redundant, but there's so many different connections that a lot of the tests that we use, you have choices. And once you find something in one way, then you don't have to really use the other tests to find it again. So if I use the second derivative test to classify the critical points, everything else is kind of given to me for free in terms of increasing and decreasing. So what I'd like to do is I'd like to show you an example similar to one of the ones we looked at last time, honestly. So not one that's super complicated, but one that is, somewhat interesting. And we will see why this method is really quite powerful, why this second derivative test is so nice, okay? And it's going to be, I think you'll find it very interesting how easy this is to do compared to what we did last time. Not that what we did last time was all that difficult necessarily, but I personally find this easier. Now, if you find this harder, okay, some people for some reason might find one of these techniques more difficult, and that's fine. But hopefully you will agree with me that this saves us some time and makes things a bit simpler. All right, so let's say that we want to work with the function f of x is equal to x cubed plus 6x squared minus, let's say, 9x minus 1. And I want to classify the critical points, find the inflection points, and find the intervals of increase, decrease, and concavity. So this is like 6 different things, 5 different things that I want to find here, okay? A lot of problems are going to ask us for this. And then let's suppose that we even want to use this to make a sketch of the graph. Well, here's what we're going to do. We're going to start by taking the derivatives. So f prime is 3x squared plus 12x minus 9, and f double prime is going to be equal to 6x plus 12. There we go. For some reason, I'm having trouble doing basic multiplying by 1 here or something. Now, the critical points, if I set this equal to 0, 3x squared plus 12x minus 9 equals 0, well, this is the same as x squared plus 4x minus 3 equals 0. Now, I think we actually did this problem last time using the first derivative test, which is fine. I want to show you something, like I want to do a similar thing, but showing you with the second derivative test. So I don't remember if it was exactly this example or if it was just similar, but either way, bear with me here. So, does this factor? No, it does not factor. So we're going to have to use the quadratic equation, or quadratic formula, excuse me, to figure this out. So we're going to have -4 plus or minus the square root of 4 squared minus 4 times 1 times -3, all divided by 2 times 1. This is going to be -4 plus or minus square root, let's see, 16 plus 12 is 28 divided by 2. This is going to give me, let's see, this is actually -4 plus or minus 2 radical 7. And so we end up with our critical points, which I will record up here. These are going to be -2 plus or minus radical 7. Yeah. Now, we want to classify these as maximums or minimums. So I got to figure out, if I want to use the second derivative test, I have to figure out whether or not the second derivative is positive or negative at each of these points. Well, here is what I can do in order to do that, okay? So first of all, I'm going to erase the actual question up here so that I have a bit more space, because this is a tiny whiteboard and it's kind of annoying, but keep in mind what the problem is we're doing. So here is my number line. I'm going to mark my critical points. -2 minus radical 7, -2 plus radical 7. We will mark that this is a critical point in each case. We may as well also find where the second derivative is equal to 0, because that's going to tell us the inflection points possibly, or it tells us where the inflection points could happen. Well, 6x plus 12 being equal to 0, this has the solution x equals -2. Now here's what I know. -2 sits exactly halfway between these two in this case. So this is actually going to be an inflection point, because notice, this is a straight line. And it goes from negative to positive. Therefore, it really does change signs at x equals -2. And therefore, what we can say is this is a real inflection point. Furthermore, we are concave down on the left of it, and we are concave up on the right of it. Because on the left, the second derivative is negative, and on the right, the second derivative is positive. But now, look at this. I now know, without even really having to plug this value in, that because this critical point sits in a place where we're concave down like this, this is actually a local maximum. And this is actually a local minimum. And now, from that, I can immediately tell you where the intervals of increase and decrease are. So, let me erase this work that we did down here, because we've got everything recorded now. So make sure you copy this down if you need to pause and take a minute. So now what we can say is f is going to have a maximum at -2 minus radical 7. It is going to have a minimum at -2 plus radical 7. And it is going to have an inflection point at -2. It is going to be concave down on -infinity to -2, concave up on -2 to infinity. It is going to be increasing on -infinity up to -2 minus radical 7, unioned with -2 plus radical 7 up to infinity, and it is going to be decreasing on -2 minus radical 7 to -2 plus radical 7. I said 6 things, but apparently we're actually looking for 7. Although I guess you could say, like, the concavity intervals, that's really one question. The intervals of increase and decrease, that's really one question. Now, if you want to use this to make a sketch, here's the ways that you can do it. You take all of this information, and then you might want to get some additional information as well. Like we can see here that the y-intercept is going to occur at -1. And you might also want to plug into a calculator and get like an estimate at least of what happens at the maximum and the minimum, but it's kind of up to you. I'm not going to make this that great a sketch because I'm just doing a really quick sketch. But here's what we do. Here's our -2. That's where our inflection point is going to be. And the square root of 7 is somewhere between 2 and 3. So back here is where we're going to have our maximum happen, and then somewhere over here is where we're going to have our minimum happen. And then what I'm going to do is I'm going to draw something that comes up to a maximum and continues curving downwards on this side. And it's not going to necessarily curve down. I'm sorry, I'm having some really hard time drawing this for some reason. It's not going to curve down necessarily too fast because we are going to go through this place at -1. And here's where the inflection point happens and we start curving upwards again. Okay, so I don't know exactly where that happens. Well, you could plug in -2 and see exactly where this happens if you wanted to, by the way. I'm just being kind of lazy and quick about this. And then we hit our point here and we hit our minimum and we continue going upwards and curving upwards for the rest of the way. So this is not going to be a very precise graph, but it's reasonably accurate, at least in terms of its shape. And as I say, we could make this a little bit better. We could do things like we could calculate exactly what the maximum is, right? We could plug this in. I'm just being lazy about it. And we could plug in the inflection point, find out exactly what happens here. We could plug in the minimum and see where that happens, that kind of thing. So there's more information that you can get. The other thing is, of course, we do need to worry, like, what if we have asymptotes? So you may need to look for horizontal and vertical asymptotes depending on what's going on. And in this case, we don't have any because, well, we certainly don't have any vertical asymptotes. And also, this is a polynomial. So as we go off towards the edges of the graph, this thing either goes up to infinity or down to -infinity, and that's it. There's no other things that we can say. So there we go. We've been able to figure this out. So I will note here that when you are sketching a graph, the other things that you need to look for, which didn't apply in this problem necessarily, but they do apply in general, the other things that you're going to want to look for are things like asymptotes, okay? And that's going to be really important and something that we're going to deal with a little bit later, okay? But for now, we're just going to leave things be. Well, for some things, we're going to be able to calculate the asymptotes, but there's other techniques for asymptote calculation that we will come to later and see how they work out, because some problems we can calculate asymptotes, but it's not necessarily obvious yet. Okay, so let's suppose now that we want to deal with a slightly more complicated problem where we do, in fact, have some kinds of issues going on. Like, let's say, for instance, that we have the same kind of question, but for f of x is equal to x squared minus 1 divided by 2x plus 4. So I want to do the same problem, but in this case. Now, the first thing that I'm going to want to do is to identify the fact that the domain is x not equal to -2. In fact, we are going to get a vertical asymptote at x equals -2. And in fact, we can see that as we come in from the left-hand side to this vertical asymptote, well, from the left-hand side, the numerator is going to be positive, the denominator is negative, so the fraction is negative, and as we come in from the right-hand side, the numerator is positive, the denominator is positive. So we can see that the limit as x approaches negative 2 from the left of f of x is negative infinity, and the limit as x approaches negative 2 from the right is positive infinity. And if you're forgetting this kind of thing, go back and review the section on infinite limits, okay? Because we covered this sort of thing a while back, and you may not remember it so well at this point because it's been quite a bit of time. It's back in chapter 2. So that's the first thing I want to do. Now, the next thing I want to observe is that in terms of its end behavior, well, the numerator is a higher degree than the denominator, and it is degree 1 bigger, and therefore this thing is actually going to end up with an oblique asymptote. If you remember back from pre-calculus, the idea of oblique asymptotes. And but we're not going to worry too much about the oblique asymptote because I didn't ask that in the last question. That's just another thing that we can use when we're sketching graphs. So now what we can do is we can take the first derivative and the second derivative. F prime is going to be equal to, now I do need to use the quotient rule here. So remember, this is f prime times g, so 2x times 2x plus 4 minus g prime times f, so that's going to be minus 2 times x squared minus 1, and all of that is going to be divided by 2x plus 4 squared. Let's see if we can simplify this at all. So this is going to become 4x squared plus 8x minus 2x squared plus 1. So that actually brings this down to a 2x squared plus 8x plus 1 divided by 2x plus 4 squared. So now what I can do is I can say, okay, well, if I want to take the second derivative, oh, this is going to be a nasty one, isn't it? In terms of finding these things. We may end up actually solving this using a computer because we're going to end up with quite the ugly little mess here. So the second derivative is going to become, I did not think this problem through before I put this down. This may not have been the best idea that I ever had. If we take the second derivative here, this is going to become 4x plus 8 times 2x plus 4 squared minus 2x squared plus 8x plus 1 times 2 times 2x plus 4 times another 2, all divided by 2x plus 4 to the fourth. Okay, so that is rather nasty. You know what we're going to do is we're actually just going to simplify this using a computer algebra system to save us some time. Okay, so after simplifying this all down, we actually get something nice. So thank goodness, the example actually works out okay. As in, it's not going to be quite as annoying as I had feared. So it comes out to be 56x plus 112 divided by 2x plus 4 to the fourth. Okay, now here is the good news. We really don't have such bad things to deal with here in terms of finding the critical points, the possible inflection points, and things like that. So you'll notice here that the only place where the second derivative could be equal to 0 is actually going to be when 56x plus 112 is equal to 0. That means x is equal to negative 112 divided by 56. That is actually negative 2. I didn't intend for this to come out the same as the last problem, but hey, it did. That's happened. I mean, it happens. Total coincidence, but there we go. And is this an inflection point? Well, the answer is yes, it is an inflection point. And the reason it is an inflection point is because the numerator changes signs at this point and the denominator does not. Now, you'll notice that another place where you can have concavity change is at breaks in the domain. So if I have a break in the domain like I do at this vertical asymptote where this is not in the domain, I can change concavity there. But in this case, I do not. The reason is because, well, actually, no, in this case I do, don't I? Because this is not an inflection point. Ah, yes, okay, I see, I'm sorry. This would be an inflection point, except it's already actually not in the domain. Oh, yes, I see what's going on here. Yeah. So this is actually, you can factor out an x plus 2 here, and this is actually 2 times x plus 2, so you can cancel one of them off. Yeah, okay. Okay, that's interesting. Anyway, don't worry about that. I'm just fascinating myself with algebra in this problem. The point is, this would be an inflection point normally, except that's just the break in the domain. So that's all we've got going on here. So what's going to happen here then is that we are going to be concave down from minus infinity to minus 2, and then we're going to be concave up on minus 2 to infinity. So then what we can do is we can solve for f prime being equal to 0. Well, this is equivalent to just solving the numerator being equal to 0. And I'm going to get rid of this second derivative stuff because we're done with it for now, but hopefully you have it written down at this point. If I take 2x squared plus 8x plus 1 and set that equal to 0, and then I go ahead and solve it. You know what? I'm going to be lazy again and just throw this into the computer because we've done enough of this stuff that I'm comfortable just doing that with you at this point and not showing you every single detail. And that saves us a little bit of time here. We get minus 2, or actually, I'm sorry, x equals minus 4 plus or minus the square root of 14 divided by 2. So that's just coming obviously from the quadratic formula. And then we have this question of, okay, so which of these is a minimum, which is a maximum? Well, notice this is negative 2 plus or minus the square root of 14 over 2. So we're going to end up, since we're concave down to the left of negative 2, if we make our little number line here, right, we have negative 2. This is my vertical asymptote. Negative 2 minus radical 14 over 2. We are concave down in this region, and therefore this is a maximum. Whereas over here at negative 2 plus radical 14 over 2, well, this is going to be our minimum. Because, I'm sorry, this is concave up over here, therefore this is a minimum. And we can now do our intervals of increase and decrease as well, because we know that we are going to be increasing up to our maximum, then we're going to be decreasing. Now, you can change increasing to decreasing in a vertical asymptote, but in this case, it happens to be decreasing on both sides. And then we start increasing again. Now, one thing you do got to be really watch out for here, though, is that you're not decreasing from negative 2 minus radical 14 over 2 all the way to this minimum. No, you're decreasing until you hit the vertical asymptote. You skip over the vertical asymptote because that is not in the domain. So it doesn't make sense to talk about the function increasing or decreasing at negative 2 at all. It doesn't exist at negative 2. So when I write my intervals of increase and decrease, and I'm going to have to get rid of the derivative now at this point too, I'm going to have to say that I am increasing on minus infinity to minus 2 minus radical 14 over 2 unioned with minus 2 plus radical 14 over 2 up to infinity, I am decreasing on minus 2 minus radical 14 over 2 up to minus 2, unioned with minus 2 up to minus 2 plus radical 14 over 2. Wow, okay, a lot of radical 14 over 2 things happening here, but what I really want to emphasize here is we are skipping negative 2 because it is not in the domain. Really important. Okay, did we write everything down now? We basically did. We just have yet to say that we have, so we have the maximum here, we have the minimum here, and we have no inflection points. So there we go. Okay, so I promised you last time that I was going to show you one of these more complicated questions that involves a rational function. Now here's the kind of the problem here with these things. All sorts of things can happen. I can't show you one example of every possibility that's going to happen for you. So here is what I'm going to ask you to do. I would like for you to go to Paul's Math Notes, the website, okay? Well, first of all, I would like you to read the book. So, chapter 4.3 in your book. But I would also like you to go to Paul's Math Notes, and I have the link on Blackboard for you, and look at the things that he has about the first and second derivative tests and examples of using it, because I want you to see more examples of things that can happen. Now, the other important thing is, of course, practicing them yourselves, because you'll start to see all the different types of things that can happen, and you just kind of have to get used to them as you go. So, like I said, the problem is I can't show you an example of every single little variation that can come up. Okay, you're going to have to sort of use the rules to reason through them on your own. But once you see more examples, you start to recognize common patterns and things like that. Okay, so that should help you. Now, here's what I do want to say, though, about other examples. What if instead of having something like this, what if I'd had the following? So what if I had instead given you this function, f of x is equal to x squared minus 1 divided by e to the x minus 1. We could actually classify, we could find the maximums and minimums, we could find the concavity, we could do all of that stuff right now. But here is where we would have some trouble. How would we find the endpoint behavior? What is the limit as x goes to infinity of f of x? What is the limit as x goes to minus infinity of f of x? All of the other information we could actually figure out quite easily. For instance, we know that this is going to have a vertical asymptote at 0, because that's where the denominator is 0 and the numerator isn't. We can figure out its behavior near the vertical asymptote, and you can go ahead and find the maximums and minimums. You can even find the intervals of increase, decrease, and concavity. In fact, maybe you want to go ahead and give that a try and see what happens. I'm pretty sure it comes out to be not too bad. Maybe it does come out to be kind of ugly. Actually, so I take that back. Don't necessarily try this one until I've thought about it more. But what I want to emphasize is, how would we find these behaviors at infinity? Well, the answer is we don't really have a good way right now, because we know how to find those things for rational functions. It's not too difficult for rational functions. We can kind of do the whole thing with algebra. However, in this case, we have an e to the x in the denominator, and that means that we are not dealing with a rational function. We're dealing with something else. Well, there is a way to deal with this, and it's something that we're going to be dealing with pretty soon. So I just want to tell you, we will be working out how we do these kinds of problems, just not yet. So stay tuned, and we will come to this later. All right, so I think this has gone on for just about long enough here, and you're probably getting kind of tired watching this video. So, and when you're watching these videos, obviously you can take breaks, pause it, take a 10-minute break, get a snack or something, come back when you're feeling refreshed and things. One of the nice things about having the videos like this is that you can do that. You're not forced to always do the whole thing in one sitting or whatever. But
Yeah, so we will come back to this kind of thing. I'm not going to do any more videos this week because you do have your upcoming test. And so, normally we would have the test in class, and therefore you wouldn't have as many lectures this week anyway. So you get a little bit less lecturing this week, but you do have to do a test. All right, so let me know if you do have questions for the test. Make sure that you look at the practice problems for the test, and then the test will be coming open this week. And yeah, so follow the instructions on Blackboard, and good luck.